Hello guys, today in this video we are going to discuss about velocity versus time graph when the object falls freely and under the influence of gravity, and when the object falls in air, then I mean with of course the air drag or air resistance, whatever you said. Then what will happen to the velocity versus time graph or acceleration versus time graph, right? So acceleration versus time or velocity versus time, that we are going to see. Anyways, for free fall it is simple. You know that the acceleration is constant, and we said this is 9.81 meter per second square. The object is falling freely, so the center of mass is experiencing only one force, that is your mg. So you got F net is equal to your mg, the weight. So ma is mg and your a value is g, right? So this is a constant acceleration. So if one would plot the acceleration versus time graph, it will be constant throughout, and this value we said is 9.81 meter per second square, right? And accordingly one can also plot the velocity time graph. So velocity time graph will be like continuously increasing with a constant gradient, and is given by, this gradient is given by your 9.81 meter per second square. Okay, meter per second square, right? This way we wrote for free fall. Now what we will do if there is some air resistance. Okay, so if there is some air resistance, then you consider the object like this, the center of mass of the object, and the weight acting downward mg, and let's take the drag force is upward, like, let me just write this to be fd. And we know that the drag force will increase proportionately with velocity. For relatively low velocity, for very high speed or velocity, you got fd is proportional to v square. Let us consider this in our case, fd is proportional to v, right? So with respect to time, the velocity will increase, and as the velocity will increase, the drag force will also increase. Okay, so the net force here, if you'll see F net, you can see is actually F net is equal to your mg minus the drag force fd. Now what is this fd? If I'll just remove the proportionality constant, I can write this to be a damping constant b. Damping constant depends upon the medium in which that object is actually dropped. So b times v. So this is what we wrote. This is the magnitude of the drag force, and the direction, as we know, like in it's opposite to the velocity or the motion of the object. Okay, if the motion falls downward, then the resistive force will be upward. So substitute. So mass into acceleration is the net force. Now here you got, this mg, and this is b times v, right? Let us now further solve it. Like I can write a is equal to g minus b by m times v, dividing m or cancelling m from all the sides. So this way we can write. Now this acceleration is actually dv by dt, which is equal to g minus b by m times v, right? So now I will just rewrite this right hand side this way, taking b by m common. What we can write? g times m by b, so that b can be cancelled, can be cancelled, and we will get the g back. So and then this is v. Okay, so here this v is the function of time, which changes with respect to time, as the object is falling. So the velocity will keep on increasing with respect to time, right? So this is what we got. So finally we have like dv by dt is equal to b by m times gm by b minus v. This is the differential equation one would solve to get the value of velocity as a function of time. So to solve this, what we are going to do is, let us consider a function, auxiliary function p, as a function of time, which is gm by b minus v, right? This v is of course function of time, this way, right? Then if we'll take the derivative of this dp by dt, let me just do it here. Okay, so if I'll take dp by dt, Okay, then gm by b is constant, g constant, m constant, b damping constant. So we will get dv by dt, right? Okay, this way. Now let us substitute in this original equation, the boxed equation. So now dv by dt can be written as the boxed equation as minus dp by dt is equal to b by m, and then this bracketed term already we have considered it to be p, right? So b by m, and this is your p, which is the function of time. Well, now here if you'll see, this equation actually gives you what? This equation, if you'll see here, it says P is actually what? Proportional to dp by dt. If you'll see this, okay, here you can write like, pt is equal to minus m by b dp by dt. So the function here pt is actually proportional to dp by dt. When this is the case, we can actually solve this equation to be what? To be actually, we can write it as pt is equal to c e to the power dp by dt is minus b by m, right? So minus b by m e to the power minus b by m t, this way we can write, right? So when the function is proportional to its derivative, you can write this way, right? So pt is equal to c e to the power minus b by mt. C here is just a random constant I have taken, and we need to calculate what is c later, right? Using correct boundary condition or desired boundary condition. Okay, so now let me just substitute all these values in the equation v. Okay, so if I'll write this and we'll substitute in this equation, like in the original equation. So pt is equal to your yeah, pt, we got c e to the power minus b by mt, right? So we can write this to be mg by b minus v is equal to pt. So that's the value we have already considered for pt, c e to the power minus b by m mt, right? So from this we can write v is equal to, taking this side, and here we got mg by b minus c e to the power b by m and t. Okay, so further let us now find out the value for the c, the random constant. Okay, in the integration we considered. So let us put the boundary condition. What is the condition? T is equal to 0 when the ball is dropped, when the object is dropped from a certain height, that is considered to be t is equal to 0. The velocity is also 0. It is dropped from rest, right? So if we'll substitute it, 0 is equal to mg by b minus c e to the power, this is b by m into t, t is 0 here, so you got e to the power 0, so that's whole thing is 1. So we got c is equal to mg by b. Simple, right? Let us now substitute the value of c and rewrite the original equation for velocity as a function of time, right? So we can now write velocity is given by mg by b. The value of c that we got is minus mg by b e to the power minus b by m times t, right? So the mg by b you can take common, and you can write 1 minus e to the power minus b by m t. Okay, this value. Now this is very simple. If you want to like substitute some random values, suppose I'm just writing it here. You can see m is constant, g is constant, b is constant, so some constant multiplied with 1 minus e to the power minus b by m, this ratio is also constant, and t, right? So here you got this as velocity, right? Suppose you are considering m is suppose you're 10 kg, and g is, for example, 10 meter per second square, and b is suppose 0.1 or something like this, right? these values I'm just randomly writing. So you can like velocity is a function. If you write 10 times 10, that is 100. Okay, let us make it 1 kg just for simplicity. Okay, so 1 kg, so 1 into 10 divided by 0 0.1, so you got 100. And 1 minus e to the power, this is minus b by m, that is 0 0.1 divided by m is 1, so 0 0.1, sorry, 0 0.1 with a negative sign, and t. Right now you can easily see what is the nature of this graph. Now if you plot, you take this one or just any like for a specific value I did. But yes, I'm going to plot this graph. Okay, you can use Desmos or any other function calculator, and then you can plot this graph and see what is the nature. So it is 1 minus some constant, mg by b minus mg by b e to the power minus b by mt. So the nature of the graph you will see is time, and the velocity as a function of time will be like this. It will go and will bend, will bend, will bend, will attain the terminal velocity, right? So this is what we said, the terminal velocity. That's the maximum value of velocity. Okay, so the maximum value of velocity is here. Okay, so yeah, so now if you want to find out the acceleration from this, okay, so the velocity time graph we got from the equation that we defined. Okay, from here you can see the equation that we got. This can be plotted to show the exact nature of the velocity versus time graph in air. And then if you want to find out what is the acceleration, okay, what is the acceleration versus time, then it's simple. Already you know the velocity, so you can write the acceleration value. So acceleration, if I'll write as a function of time, dv by dt, so that will give me d by dt of this term, okay, will be 0. This is a constant term, and the remaining I can write. So d by dt of this is minus mg by b e to the power minus b by m t, right? So this is in the form of k, I mean some constant e to the power minus. So you take the constant out, minus mg by b, right? And then d by dt of e to the power minus kt, right? So in this format, so you can write this to be what, taking the derivative, you got minus b by m e to the power minus b by mt. Okay, the constant term. Well, so now you can see, like, mm got cancelled, b got cancelled, minus minus plus. So we got g e to the power minus b by mt. So this gives you the acceleration, and you can see clearly it suggests exponential decay. So g is the original value. Okay, and then you can see how the acceleration actually uh, will look like. A function of t, we can write this to be g e to the power minus b by mt, right? So this way you can write the acceleration. So now you can plot the graph for the nature of the graph for acceleration versus time. So nature of the graph for acceleration you can plot this way. So suppose this is your time, this is your acceleration. You can see this is your maximum value. You can see g e to the power minus b by mt. The maximum value is g here, right? And then you can see it will decay exponentially and will be like this as the time increases, right? So g to the power minus b by mt. This is how the acceleration time varies. Okay, so now if you compare the graphs, okay, in both the cases, for free fall, your acceleration versus time graph, you got like constant acceleration, but here you got exponential decay like this. It's exponential decay like this. Okay, this is your acceleration versus time. And the velocity time for the free fall, constantly increasing with a constant slope of course, right? And vt, and here you got 1 minus the exponential decay, So here you got the velocity time graph like this. It goes and then bends, attains the maximum velocity, which we said the terminal velocity, right? Hope you guys understood the comparison between both the fall in presence of air or any damping medium, and the other one is without any medium. So what happens to the acceleration versus time, or the velocity versus time graph? Thank you.